Okay, so then let us begin. So we are very happy to welcome Schlomo Razamat from Technion for his third lecture in this winter school on aspects of supersymmetric dynamics and geometry. And I believe today's lecture will involve the geometry part, right? If I understood.
Okay, hopefully. So let me thank you, Babak, for the introduction. And related to what you were just saying, I have posted all my lecture notes on Slack. So it involves the geometry part. However, I overestimated my abilities. So today I will still be covering most of the dynamics, supersymmetric dynamics part. So we will finish the first two lectures today. And hopefully I will start the geometry also today. And anyway, the last lecture will be some kind of a combination of the two last lectures in the notes. So please look at the notes. Okay, so today I'm continuing with dynamics. So today we will discuss two interesting four-dimensional strong coupling effects. One which we started a little bit discussing in the end of the last lecture. It will be about emergence of global symmetry in a simple quantum field theory. And another one will be about conformal dualities. Okay, and again, either I will have time tomorrow to connect these observations or observations of these types to geometry. At least some of them I will be able, but all of these interesting strong coupling dynamics in four dimensions has typically some geometrical origin. Okay, so let me start with the discussion of the dynamics of a very particular example of interesting dynamics in four dimensions. So first part of this first page is basically a review of what I did in the end of last lecture. So we're looking on one of the simplest quantum field theories, interacting quantum field theories that one can consider in four dimensions. An SU2 SQCD with an F equals 4. I remind you that an F equals 4 in general means that we have 4 fundamentals and 4 anti-fundamentals. However, since we have an SU2 gauge group, fundamentals and anti-fundamentals are basically the same representation. So the theory that we have is SU2 gauge theory with an octet of fundamental fields, which we will denote by Q. Okay. This theory is asymptotically free, as can be verified by computing this 't Hooft anomaly, as we discussed. So we start in the free theory. The free R charges of the fields that we assign to Qs are 2/3, and then we compute this anomaly. So this 2 comes from the gauginos, from the vector multiplet. Then we have this contribution of the Qs. So this is the R charge of the fermionic components in the chiral multiplet. Okay, the chiral multiplet, the free chiral multiplet has R charge 2/3, but that means that the scalar component of it has this R charge, but the fermionic R charge is shifted by -1. So this is the contribution of the fermion. This is the trace of SU2 squared of a fundamental representation, which gives half, and we have 8 fundamentals. And this number turns out to be positive. As we discussed, this means that this theory is an asymptotically free theory. So we flow into infrared, and then there is a question, what is the superconformal R symmetry? And the superconformal R symmetry, the anomaly-free superconformal R symmetry is such in particular that this anomaly in the infrared equals to 0. That means that it is non-anomalous. And the non-anomalous assignment of R charge is just giving all the superfields R charge a half. Again, you can compute this anomaly, simple algebra, and you find that it is equal to 0. Okay, so if you wish, this is a mixing of this anomalous R symmetry, okay, which is 2/3, and another anomalous U1 global symmetry that you have before you turn on the gauging in the UV. Okay, so this is the theory we start with. So if you wish, our starting point in our this flow diagram is this SU2 with an F equals 4. And a collection of free chiral fields, which I denote here by MAB. Okay, and we start the flow by turning on a certain deformation, which is written here. Okay, we turn on a superpotential, which couples these 15 fields MAB to a bilinear gauge invariance of these fields Q. So what we did, we split the 8 into 6 plus 2. Okay, and then we built a gauge invariant combination of these sixes. So we need to anti-symmetrize the SU2 indices. So we also need to anti-symmetrize this global symmetry indices. So there are 15 gauge invariant operators that we can build like that. And we couple them to 15 free gauge singlet fields. Okay. Again, you can verify that this superpotential is relevant. The R charges of Qs are half at this fixed point that we start with. This is the fixed point, IR fixed point of this Lagrangian. We add free fields. So the free fields have R charge 2/3. So in total, we have an R charge for this superpotential, which is less than 2. So this deformation is a relevant deformation. And we start a flow, and we flow to some theory in the infrared. And what we want to understand is what is the property of this theory in the infrared. Okay. Notice that the theory we started with, this SU2 gauge theory, has an SU8 global symmetry because we have 8 fundamentals. But this superpotential breaks the SU8 to SU6 times SU2 times another U1 symmetry. Basically, this is the U1 symmetry, which in the decomposition of SU8 to SU6 times SU2 times U1. So the question is, what is this theory in the infrared? Well, what are the properties of this theory? Okay, and the properties of this theory are quite surprising, as we will see. And again, please feel free to stop me and ask questions at any moment that anything is unclear. Okay. So to analyze this flow, to analyze these dynamics, let's just write the table of charges of this theory. So we have these fields Q, Q tilde, and M that we have written on the previous slide. So these Qs are these sextet, the Q tildes are this doublet of this SU2, and M are these 15 fields that I have written here. And for a moment, ignore the last line, the M tildes. I did not introduce them as of yet. So again, the Qs are a sextet of SU6. And if you want to assign an anomaly-free U1 charge to these fields, the proper assignment will be assigning charge a half to fields Q and a charge minus 3/2 to the field Q tilde. This is, again, this can be easily verified that this assignment of charges is anomaly-free. Okay, now the question is, with this deformation, what happens in the infrared in terms, for example, of R symmetry? What is the superconformal R symmetry in the infrared? And as we have discussed, to understand that, we need to perform this procedure of A maximization. We choose some anomaly-free R charge, and we look on all the possible U1 symmetries that this theory has, and the ways to combine the R charge with these U1 symmetries. We define certain trial A anomaly, and we maximize with respect to the parameters. So here I perform this very explicitly. So I assign certain U1 R charges, and you can verify that these R charges are anomaly free and that they are consistent with this superpotential. And actually here I already have chosen the superconformal R charges. But you don't have to believe me. You can take these R charges that I have written here and mix them with the only U1 symmetry that we have here, the U1H that I have defined, with some coefficient alpha that I write here. And then compute this trial A anomaly, which depends on this alpha. So what is this thing? So we have a contribution of the vector fields. So we have an SU2 gauge group. And so we have 3 vectors. And this is contribution of the single vector. Then we have this contribution, which comes from the Qs. We have this contribution, which comes from the Q tildes. And we have this contribution, which comes from the Ms. So this is the trace R cubed part. And this is similarly the trace R part. So this is some function of alpha. So you now need to find the maximum of this function to find a maximization. So you just compute the derivative and equate to 0. And you find that there are 2 solutions, alpha equals 0 and minus 2/3. And it so happens that alpha equals to 0 is the maximum. Okay, so in fact, this R-symmetry assignment that we have written here is the superconformal one. Okay, so if you have any doubts, please verify this. All these simple exercises are worth performing. Okay, so we know what is the superconformal R-symmetry in the infrared, and now we want to understand what does it tell us about the quantum field theory there. So there is a first surprise that you can observe. So you look on this field Q tilde, okay, and you find that this R charge, the superconformal R charge, which you assign, which you have to assign to it, is 1/3. Okay, remember that we discussed that there is a unitarity bound on these R charges for operators in a conformal theory, which is 2/3. So here you find a charge which is 1/3. This is not a problem because this field Q tilde is gauge variant field. It is charged under the symmetry which we gauged. Okay. However, if we build a gauge invariant out of this field, basically Q tilde squared, okay, then we get an operator which has R charge 2/3. Okay. Operator which has R charge 2/3 means that it is a free field. A chiral operator with R charge 2/3 basically means that this is a free field. So what we obtain here is that the theory flows to an infrared fixed point, which might consist of some strongly coupled interacting piece, but also contains a free field. Okay, and if you remember, all this procedure of A maximization was under the assumption that we don't have any emergent accidental U1 symmetries. But if we have some operator which becomes a free field, it comes with its own U1 symmetry. We can rotate this field independently of anything else. We have an emergent symmetry here. Okay, so we should worry whether our procedure is self-consistent or not. Okay, so what we need to do, what we can do, since it is a free field in the infrared, we can add an additional deformation to the theory. And this is this field M tilde, which appears here in the last line. And what this field M tilde does, what we do with it, we just couple it linearly to this operator, which becomes a free field in the infrared. So basically, this is a mass term for this free field. We add a mass term to this free field. And again, you can verify that it is a relevant deformation. Remember, we discussed that you should analyze flows, RG flows, one step at a time. You add a deformation, analyze where you got, add another deformation, and analyze where you got. So we deformed our theory with this deformation. We got a free field, but now we can add a mass term to that free field and decouple it and flow again. And sorry, somebody is drawing on my page, or I don't know what it is. It's not me with the red line, so I don't know. Anyway, so in this way, we decouple this field, this free field in the infrared, and this procedure of introducing a chiral field and coupling it linearly to an operator and removing it from the theory is called flipping the field. Okay, this is some notation which is very common in the field. So now what you can do is, after you have removed this free field, you can redo this procedure of A maximization, now including this field M tilde. Okay. And what will happen if you do that, the assignment of our charges, which are given here, does not change. Okay, although we have this accidental U1, this accidental U1 still doesn't mix with the R symmetries, with the superconformal R symmetry. And in fact, the reason that it doesn't is that even without adding it, it doesn't really violate the unitarity bound. It saturates it. Okay. So we just remove it and then nothing changes. Okay, so this is the theory we will consider. This theory now doesn't have any free fields in the infrared. It is some strongly coupled interacting SCFT. And that properties of this theory we want to understand. Any questions?
Can I ask a question?
Of course.
Yeah, so to start with, what's the motivation of introducing this deformation? I mean, this MAB. Yeah.
Very good. So the way I presented it, it's completely unmotivated. Of course, when we originally looked at it, there was a motivation. And actually, I will come to the motivation in the end of this discussion. Okay?
Okay.
The motivation is to build a theory which has interesting properties. From what I discussed till now, you have no way to understanding or to guessing that this theory might have an interesting property. Okay? So hold this question for 5 minutes or so, and you will get an answer, hopefully.
Okay. Yeah.
Till now, it's just, we will start with simple theory and deform it and see what happens. Okay. Okay. So, okay, we got some theory. So we understand what is a superconformal R charge. Again, under the assumption that there are no accidental symmetries. Okay. Always there can be accidental symmetries that we could not identify. So this assumption is always in the background. We cannot rule it out. It might be that this is not a superconformal R symmetry, that we are missing something. But at the moment, this analysis doesn't give us any evidence that something is missing. Okay. So now what we can do, as we discussed, we have some nice RG invariant quantities that we can compute. And one of them is the superconformal index, the supersymmetric index. So we have discussed that there is a certain matrix integral representation of that index, and you can compute it. Another thing that we have discussed is that you can expand this index in these fugacities Q and P, and you can look at orders in expansion QP to the power n such that n is smaller than 1, and then this index captures the relevant operators. At order QP, this index captures marginals minus the conserved currents. Again, if we use the superconformal R symmetry. Okay. So here is the result of this computation, and I will little bit explain. So we plug this the information of this theory into this machinery of this matrix integral, and it spits out this result. Okay, so how we can understand it? So index starts with 1, and 1. Remember, index count states in this superconformal field theory weighed with some weights. So you can think of this 1 as the contribution of the vacuum state to the index. And then we have other contributions. For example, we have a contribution which comes from this QQ tilde operator. QQ tilde operator is the operator which you can build, by taking this field and this field. It's gauge invariant, and it is in a fundamental representation of this SU2 and fundamental representation of this SU6, and it has certain charge under the U1H, which you can compute using the table before, and that charge is equal to -1. So when we compute the index, we turn on fugacities for various symmetries. So fugacity for U1H, we call it H, unsurprisingly. So we weigh this operator with H to the -1. Another operator which contributes at this order is the operator M, the gauge singlet operator M. That operator is a singlet under SU2 and is in the 15-dimensional representation of the SU6, since that operator couples to this to Q square operator, which is in a we anti-symmetrize these indices A and B to get a gauge invariant operator. That is 6. The anti-symmetric square of 6 is a 15-dimensional representation. That's why MAB is in a 15-dimensional representation. And again, the U1H charge of this operator is -1. So you get these operators at this order of the expansion of the index, and this number is smaller than 1, so it is a relevant operator. And you get another operator coming from M tilde with U1H charge +3, and you get a bunch of other operators that I don't write. Okay, so till now it doesn't look very interesting. But now let us look at order QP, where we should get marginal operators minus the conserved currents. So you perform this computation, and that's what you get. Okay, you get that the only terms in the index that you see are negative. Okay, all the signs that you see here are negative. This term comes from marginals, which come with a plus sign, and conserved currents, which come from with a minus sign. So all these terms should be part of conserved currents of the global symmetry of the infrared fixed point. This is easy to understand. This is the SU6 conserved current. This is 35 is the joint representation of SU6. This is SU6. This is the three-dimensional SU2 joint representation. So this is the conserved current of the SU2. This is the conserved current of the U1. Okay? But then there is a surprise. There is another operator which contributes at this order, which is in representation, which is 20 of the SU6 and doublet of SU2. Okay? So this looks very weird. First of all, it is not a joint representation of anything, okay? And there is nothing, there is no symmetry in the UV that we can identify that has this representation. So what is happening here? So there are two possibilities. One is that we did a mistake either in the computation or in our physical assumptions. For example, that we identify correctly the U1R symmetry, the superconformal U1R symmetry. Or it has to be that all these currents combine in some way into an adjoint representation of some bigger group, such that SU6 and SU2 and maybe U1 are a subgroup of this bigger group. Okay, so let us check whether this can happen. So first of all, 35 plus 3 plus 20 times 2, just the number of operators that we see here, and we don't count this U1, is 78. Now, if you know your group theory very well, 78 is the joint representation of a group which is called E6, of one of the exceptional groups, E6. Now, it's not just that this number, when we sum up these operators, we get 78, which is a joint of E6, and a joint of E6 has, sorry, the group E6 has a maximal subgroup, which is SU6 times SU2. And in terms of decomposing the joint representations into representations of SU6 times SU2, you exactly get the joint of SU6, the joint of SU2, and then this 22 representation of SU6, SU2. So a natural interpretation of this combination is as conserved currents of the E6 symmetry. Okay. So if we identified the superconformal R symmetry correctly, what this term in the index tells us is that in the infrared fixed point, the symmetry is enhancing to an E6 symmetry times U1. Okay, this U1 just comes on the right. Okay, so this is the interesting dynamical property of this theory, which we can deduce by using these very simple RG invariant techniques. Okay. So this extremely simple theory has this rather surprising property. It has SU6 times SU2 times U1 symmetry in the UV, but it flows to an interacting SCFT with E6 times U1 symmetry in the infrared. Okay, any questions about this?
Is this a non-perturbative effect or perturbative effect?
So this statement is non-perturbative. Okay, this statement about the index is a non-perturbative statement. We did not do any perturbative expansion. Okay, we analyze the flow. We start with some UV fixed point. We go to infrared. In the middle, you can undergo some strong coupling dynamics. Okay, so the whole thing of computing such properties which are independent of RG flow is that they are independent of the values of couplings, of the strengths of the couplings, of the strong coupling scale of this theory, and so on. These are non-perturbatively exact statements. So this still can be a wrong statement because it can, one of our assumptions which go into making this deduction might be wrong. And again, the only the only assumptions that can be wrong is that to write this expression, we assumed that we have superconformal symmetry and that we identified our symmetry correctly. So if this theory flows to an interacting strongly coupled SCFT, and if we identify the R symmetry correctly, this has to be correct. This theory has to have E6 symmetry. It doesn't build on any perturbative or like that logic. It's a non-perturbative statement. Okay. Okay. So this is an interesting fact, and you can ask, why would you guess this fact? Sorry, there is an annoying red line on the slide that I see on the screen. Do you see it also? Or?
Yeah,
It's not on my screen. I don't know. It's
yeah, I
probably
see it as well. Can the person who did it maybe remove it? I mean, I don't know how to do this.
Okay.
This is a bit annoying, but yeah.
Okay, so I cannot remove it. So you see this constant on the slides. It's not my constant.
Maybe you could share your screen again.
Stop share and share it again. Okay.
Is there a way to disallow participant to draw on the screen?
Okay, I think now it's fine. Right?
No, yeah.
Okay. Okay, so there was this excellent question. How did we, or how one could guess that something interesting can happen in this particular theory? Okay, so let me address that question and relate actually this enhancement of symmetry 2e6 to Seiberg duality that we have discussed. Okay, so remember that the simplest Seiberg duality we have discussed is of this form. So you have an SUN SQCD with an F flavors, okay, and it is conjectured to be dual to SQCD with a different number of flavors. So this n tilde is equal to an F minus n. Okay, and we introduce gauge singlet fields M and couple them through this superpotential. Okay, so this is some physics which was discovered 25 years ago. It's a little bit scary. Okay, so let us go now to this particular case that we are discussing, SU2 with an F equals 4. For SU2 with an F equals 4, this is the theory on the left. It's just this simple theory. On the right, since an F minus n, when an F equals 4 and n equals 2, it's also SU2, you have very similar theory, almost identical theory, modulo the fact that you need to introduce these fields M and couple them with a superpotential. Sometimes such cases are called self-duality. It's not a complete self-duality. It's not that two sides of the duality are exactly the same. There is a difference. There are these additional fields, and they play a role. But the gauge sector, if you wish, is the same on both sides, on the two sides. Okay. So now the question is, can you understand the symmetry enhancement? Since this is like almost a self-duality, you almost get exactly the same theory, but you get something else. Can you massage the self-duality to be really self-duality, that the two theories will be the same? And you can do that. So here I just write our theory that we have drawn before, this theory, okay? But I split the 6 into 4 plus 2 in order to write this quiver with 4 fundamentals and 4 anti-fundamentals as is needed for Seiberg duality, okay? So you should think of these 4 and 2 as being part of the same 6, okay? And I add these gauge singlet fields, 15 gauge singlet fields that we have added. So this fields coming from 2 to 4 is an octet of fields. We have a field which flips the gauge invariant that you can build from this field, which adds you another field. And then you have 6 more fields which flip these guys. So in total, you have 15 fields M, which come here. And then this field tilde is the M tilde field that we have before. So we can start from this theory with additional fields and perform Seiberg duality on this collection of fields, on this theory. Okay. So what Seiberg duality will do, it will add another field here, which will couple basically to this field and will add a mass term. So this field will disappear in the infrared. It will be massive, and it also will add this field, which will appear as another field in the infrared. This is a little bit fast, but it's an additional explanation I want you to think about. But now look on these two theories. They look exactly the same. Okay, they have exactly the same collection of fields. But again, they are not exactly the same. What is different? Here, the symmetry was SU6 times SU2. I have written it here. So this forms an SU6. I just drawn it in a way which is this SU6 is not completely obvious. I split this SU6 to SU4 times SU2. And here, since it's exactly the same quiver, it's also SU6 times SU2, but this is a different SU6. You see? Here you have this SU2 combining with this SU4, and here we have this SU21 combining with SU4. So if Seiberg duality is correct, these two theories should be the same. So this theory has SU6 times SU2. This theory has an SU6 times SU2, but these are different SU6 times SU2s. So the fixed point in the infrared has to contain both of these groups. So it has to be a bigger group. And the bigger group which has these various decompositions is the A6 group. If you wish, the Seiberg duality for this theory acts as kind of a non-trivial wild transformation on the infrared theory, okay, which is just a symmetry transformation. It's not an interesting transformation. So that was the original motivation to discuss this particular theory, okay, to find something, emergence of symmetry from Seiberg duality. And a lot of games can be played of this sort, and you can arrive at similar conclusions. And in the last lecture tomorrow, I will give you another motivation to look at this theory coming from geometry. So this is symmetry that you see here can be explained geometrically also. Any questions about this?
So can we split the flavor symmetry become SU2 times FCU2 times SU2 times MSU2?
That's a very good question. So now that you understand that you can play these games, you can play these games and you can try doing that. So actually, I think when we wrote this paper a couple of years ago, we played these games, but we didn't find anything interesting. So there is a lot of things that you can do. You can add these gauge singlet fields in various ways. But there was a very interesting paper recently by Sara Pasquetti and collaborators. I think Chung Huang was one of them, and Matteo Sacchi. And they did find, did many various splittings and found interesting examples of enhancements of symmetry, exactly as you suggest. Okay.
Thank you.
Okay. Any more questions? Okay. So this was a discussion of emergence of symmetry in the infrared. And now I want to discuss a different effect, a different interesting thing that can happen in superconformal field theories in 4 dimensions, and it goes under the name of a conformal duality. Okay, so what is the conformal duality? First of all, there will be no RG flow involved in this part of the lecture. Okay, so what do? We find some theory, say a theory which I will call T1. And that theory has a conformal manifold MC. Remember, we defined conformal manifold, we computed properties of the conformal manifold, and we will do a very detailed example, a different very detailed example in a moment. And on this conformal manifold, what does it mean that we have a conformal manifold? That means that this theory T1, which is defined in a certain way, has exactly marginal deformations. And any theory on this conformal manifold can be reached by deforming this theory T1 with some exactly marginal deformation. So any point on this conformal manifold can be thought of starting from this theory T1, adding an exactly marginal deformation with some value of the coupling, and that will be the point on this conformal manifold. So what is a conformal duality? A conformal duality is the situation if we have another description T2 and completely independent description of this original description T1 plus a deformation of some other point of the conformal manifold. Okay, the point here is that the two description need to be useful in some sense. Okay, it becomes tautology otherwise. Okay, it has to be this other description has to be some independent way of writing the theory. So for example, one way to proceed is that here you have one type of a Lagrangian, and here you have completely different Lagrangian. Or, as we will see, you can define this theory in certain geometrical way, and this theory in certain way with fields and Lagrangians or something like that. Okay, but if you have two or more such useful descriptions, they are obviously dual to each other in the sense that any point on the conformal manifold you can describe either as a deformation of this point or as a deformation of this point. Okay, and the canonical example of such a conformal duality is a well-studied n equals 4 super Young Mills, say with gauge group SUN, and then you can reach different points on the conformal manifold n equals 4 preserving conformal manifold of this theory by tuning the gauge coupling. And there is another description in terms of a very similar gauge group, slightly different with this mod Zn, and with a different value of coupling. So say if you are close to this point here, this tau is weakly coupled, but if you are using this description in this case, the gauge coupling that you need to turn on starting from here will be strongly coupled. Okay, so this is the effect of, this is the notion of conformal duality. Is this clear? Okay, so now the question that we will ask and we will answer is the following one. Say somebody gives us a conformal field theory that we will call T1, okay? And by gives us, I mean either gives us a Lagrangian or defines this theory in some abstract way. It doesn't matter. What matters is that this person who defines this theory provides us with some information about this theory. For example, this person tells us what are the A and C anomaly of this theory. And again, I stress that we are in 4D and the n equal 1. I will not say it every time, but this is our basic setup. So in particular, in this setup, A and C conformal anomalies are related to Wolff anomalies of the R symmetries. This person also tells us, say, what is the dimension of the conformal manifold of this theory? What is the symmetry preserved on the generic locus of this conformal manifold of this theory? What are the Wolff anomalies of these symmetries that are preserved? Say also in a good situation, this person tells us what is the index of this particular theory, okay? And what is important about all of these pieces of information, as we have discussed, they are independent of continuous deformations of the theory. If the theory flows, they are independent of the flow. And if here the theory is not flowing, they're independent of the couplings of the theory, okay? So we call this, this information MC invariant information about the theory. And then the question we ask, is it possible that this theory has a conformal dual theory, which we call T2, which we can write with some Lagrangian, with gauge fields and matter fields, such that this description will be conformal. It will directly sit on this conformal manifold, not flow to it, but you just smoothly turn on the couplings and move on this conformal manifold, okay? And the important thing is that this very little amount, this very small amount of information, this MC invariant information is actually sufficient to find candidates for such conformal duals or rule out existence of such conformal duals, okay? And the algorithm is very simple. We'll now discuss it, and then we'll give a very detailed example. Any questions about the question and the answer?
Just for the example you gave, is assume T1 is for super Young Mills theory, and the T2 is the n equals for super Young Mills, so SUN or quotient Zn.
That's
if
right.
If T1 is in the free limit, what is T2?
In the it will be in the infinite coupling limit in that particular example. Okay.
Okay.
That's the S duality of the SUN super Young Mills. So as you know, that S duality, or you might know that S duality has a geometric meaning also. We will get to it hopefully next time. Okay.
Okay.
Okay. So what is the algorithm? The algorithm is extremely simple. So somebody gave us this theory T1. So this person, as we demanded that the words gave will include telling us what the conformal anomalies A and C are. So we know the A and C anomalies. Okay. Now we assume that this theory, the same theory, is described by some free vector fields and free chiral fields at some point on the conformal manifold. Since A and C anomalies in n=1 conformal field theories are invariants of the conformal manifold, then we should be able to express these A and C anomalies in terms of contributions of free gauge fields and free vector fields. Okay, as we have discussed, the free vectors contribute in some way to the A and C anomalies. I call these contributions AV and CV. And the free chiral fields contribute some numbers. Say this is 1/48, and this is 1/24, this is 3/16, and this is 1/8, if I'm not mistaken. Okay, these are some very well-defined numbers. So it should be that we can find some integer here, which I call dimension of the gauge group, which is number of the vectors of this free conformal description, and some other integer, which is dimension of the representation, which is just the number of chiral superfields, such that both A and C anomalies will be expressible in terms of the same numbers. Okay, so basically we can translate A and C into two integers, dim G and dim R. Okay, it can happen that these numbers turn out to be fractional for a given theory. If these numbers are fractional, you are wrong. Or basically what it means, you are ruling out the possibility of the existence of conformal Lagrangian for this theory. It just cannot happen. If that Lagrangian would have existed, it should have had fractional number of vectors and fractional number of chirals, which is impossible. If these numbers are integer, you have a chance that there is a dual theory. So then what you do, you just scan through all the possible Lagrangians that you can write, which have this dimension of the gauge group and this dimension of the representation, and such that these Lagrangians are conformal, because that was an assumption of the whole procedure. There is always a finite list of such theories, and we will do in a moment a detailed example. So these theories, then, this finite list of theories are candidates to be duals of your original theory. And then in the next step of this algorithm, you just look on all the other types of MC invariants and compute it for every theory in this list of theories, finite list of theories. And if all the MC invariant information agrees with what you want, you have a candidate of a dual. Okay, as it is the case with Seiberg duality, I did not stress it, but I should have. We don't have a proof of Seiberg duality. Seiberg duality is checked in extremely many different ways, but we still don't have a proof of it. Okay, it's a conjecture. And also here you will generate a conjecture of a conformal duality of a gauge theory, which will be dual to your original theory, or you will rule out the existence of such a theory. Okay, is this clear? Okay, so now what I will do, I will apply this algorithm to a very simple case of a theory T1, which will take to be Lagrangian. We will not take some more complicated definition of the theory coming from geometry. Later on, if I will have time today, or we will do it already tomorrow, we will repeat this procedure also for some more sophisticated definition of T1 through geometry. Okay, but let us first do in detail an example, which we can do from start to the end in great detail when the theory T1 is Lagrangian, and we'll find the theory T2, which looks completely differently. Okay. So what is the example that I'm going to discuss? So we will take this theory T1 to be an SQCD with the G2 gauge group. Okay, there are several reasons why I chose this example, although I could have chosen others. Well, one reason is that the analysis here is rather simple, maybe the simplest. Another one is that at this stage in physics and so on, we should not be afraid of more complicated groups than just SUM. We already have seen an E6, so now you see a G2. Okay, G2 is an exceptional group, but it's actually a very nice group. So the theory T1 will be a G2 SQCD with this particular matter. So G2 is a gauge group, is a 14-dimensional gauge group. The dimension of the group is 14. That means that the adjoint representation is 14-dimensional. It's a rank 2 gauge group. It's a rank 2 group. It has a maximal subgroup, which is SU3. For example, the 14, the adjoint of G2 can be decomposed into 8 plus 3 bar of SU3. Okay, and the fundamental representation of G2 is 7-dimensional. And what we do, we take a triplet of fields which will denote Q, which will be in a fundamental representation, this 7-dimensional representation of G2. Again, if you want the decomposition in terms of SU3 maximal subgroup of this of G2, this will be just a 3 plus 3 bar and plus a singlet. And we also add another field, which I denote here by Q tilde, which is in 27-dimensional representation of G2. Okay, this representation appears if you take symmetric square of 7, you will get a 27 in the decomposition of the symmetric square. Okay, so this is some matter content. Okay, and now we should ask ourselves whether this theory is conformal, for example. As you remember, to determine whether it is conformal or not, first thing we need to do is, well, it's a gauge theory. We need to understand whether the beta function for the gauge theory is marginal or not. Okay, so for that we can compute this 't Hooft anomaly, and this is a simple computation which is written here. So again, this 4 is the quadratic Casimir of the adjoint representation of G2. 1 is the quadratic Casimir of the fundamental representation. 9 is the Casimir for the 27-dimensional representation. We are at the free fixed point. So again, the R charges are 2/3 and 2/3 minus 1 because we're interested in the fermions. This 3 is because we have a triplet of fundamental representations. You compute this anomaly and you find that the beta function, this one loop contribution to the beta function, vanishes. Okay, so this is a marginal, the gauging is marginal in this case. Okay, this is very similar to SUN with 3N flavors that we have discussed. And as we have discussed it there, this fact by itself doesn't guarantee that this coupling is exactly marginal. If we just have gauge couplings and no superpotentials that we can turn on, this will be marginally irrelevant deformation. So we need also to find some other superpotential couplings. Before doing that, let us say what is the symmetry of this theory. So there is an SU3 rotating the Qs, and there is another symmetry, U1 symmetry, under which the Qs and Q tildes are charged. So we can assign a charge +1 to the 27 to Q tilde and charge -3 to these Qs. And this symmetry you can check is non-anomalous symmetry. So now what are the marginal superpotentials we can turn on? Since the R charges of all the fields are free, are 2/3, its marginal superpotentials are should be cubic gauge invariant operators. So there are actually 4 types of operators that we can turn on. First of all, we have these fundamentals, and from these fundamentals we can build an invariant of G2, and we can turn it on, and with some gauge coupling, with some superpotential coupling lambda 0. Under this SU3 times U1 global symmetry, this is a singlet of SU3, and it has charge -9 under this U1. Now for G2, interestingly, this 27-dimensional representation has 2 independent cubic singlets that you can build. This is in a sense similar to, say, if you have an adjoint, say, of SU4, you can build 2 independent quartic singlets from quartic powers of this adjoint representation. So this is non-intuitive, but you can think of it as just in some way contracting the indices in a different way. So there are two couplings that we can turn on, which are we call lambda1 and lambda1 prime, which are singlets of SU3, since this Q tilde is not charged under SU3, and they have the same charge +3 under this U1 symmetry. And finally, we can build a cubic coupling, which uses both Q tilde and Q, and it is written here. It's Q tilde times Q, where these indices, the SU3 indices of Q, are symmetrized. So this guy is in 6-dimensional representation of SU3 and has a charge -5. So we have a lot of marginal couplings. So there is a chance that this theory has a conformal manifold, and we will compute it now. Okay. Before computing it, I just, a trivial comment that of course we can compute A and C anomalies for this theory. We have 14 vectors. This is a G2 gauge group. The number of fields, the number of matter fields is 27, coming from the 27-dimensional representation, and we have 3 fundamentals. So total number of fields is 48. So dimension of the group is 14. Dimension of representation is 48, and using this information, you can compute the conformal anomalies. So now we turn on to analysis of the conformal manifold. So as we have discussed, to analyze the conformal manifold, we need to list all the marginal couplings, which I have written again here, and we have to compute this quotient by the symmetry group at the free point. I stressed to you when we discussed the SU and SQCD that you need also to take into account anomalous symmetries and gauge couplings. Here I don't write them because, again, as we have seen there, if you have superpotentials, you can always win this game with anomalous symmetries and gauge couplings, and you always, in this quotient, the gauge couplings cancel against anomalous symmetries, at least in simple cases, and that's the case here. Okay, so we only consider this quotient. So how do you compute this quotient? So one way to compute this quotient is to find all the holomorphic invariants that you can build from these couplings. Okay, so you can start with the couplings lambda 0, lambda 1, and lambda 1 prime, since they are singlets of SU3. Okay, so you only need to build singlets, independent singlets, or charge 0 combinations under the U1 symmetry. And it's very easy to build 2 independent contributions, lambda 0 times lambda 1 cubed and lambda 0 times lambda 1 prime cubed. Okay. This type, if you turn on only these couplings, since they are not charged under SU3, you don't break the SU3, but you do break the U1 since they are charged under the U1. Okay. So these deformations give you a 2-dimensional conformal manifold on which SU3 symmetry is preserved, but U1 symmetry is broken. Okay, you can analyze this conformal manifold next. The remaining coupling that you have is this lambda 2, which is in 6-dimensional representation of the SU3 symmetry group. We now can think of going on this 2-dimensional conformal manifold, and we have already broken this U1 symmetry, which we should not worry about it. We only need to find some combination which is singlet under SU3, and such a combination can be found when you think of this as just usual matrix of SU3, a symmetric matrix of SU3. The determinant will be such an invariant of SU3. Now, the question will be, if you turn on this deformation, what is the symmetry which is preserved? And actually, when you turn on such a coupling, you don't break SU3 completely, you break it down to SU2. And here you can perform a very similar analysis to what we did with SU and SQCD. You look on this marginal operator, which is in 6 of SU3, and you see how it decomposes under this preserved SU2. So the claim is that this SU2 is such that the 3-dimensional representation, the fundamental of SU3, is the adjoint of this SU2. So under this decomposition, 6 becomes a 5 plus a singlet, the 8 becomes a 3 plus a 5. And if you remember, in order for this claim to be consistent, you need to cancel, since you want to be left with the adjoint of SU2, the rest of the adjoint representation of the SU3 needs to be eaten by something in the marginal couplings. and you have exactly the same representations. So in the end of the day, this contributes to you a one-dimensional exactly marginal deformation, and you have this conserved currents of SU2. So the final claim is that this theory has a dimension 3 conformal manifold, 2 directions coming from here and 1 dimension coming from here. And on generic point of this conformal manifold, the symmetry is not completely broken. You have an SU2 left. Okay. Any questions about this analysis? Okay. So before looking for a dual, since we have a symmetry left, this SU2 symmetry left, we can also compute its 't Hooft anomaly. Okay, the only interesting 't Hooft anomalies is trace R times SU2 square for this particular symmetry. We also can compute the index, and we will quote the index later on when we'll compare to the dual. So the computation is very simple. Again, look at this theory. On a generic point of the conformal manifold, we break this SU3 symmetry into SU2, such that, again, a 3-dimensional representation of SU3 is the adjoint of SU2. So you can think of this triplet of Qs as being in the adjoint representation of preserved SU2. So you have here, since this is a 7-dimensional representation of a G2, you have 7 adjoints of SU2. So that is the 't Hooft anomaly that you will get. Again, this is the quadratic Casimir of the adjoint representation of SU2. This is the R-symmetry of the fermion in the free chiral field. And we have 7 such adjoints. So this is the 't Hooft anomaly, trace R times SU2 squared, 't Hooft anomaly of this theory. Okay. So these are all the MC invariant information that we need to look for a dual theory. Okay. So now we will apply our algorithm to seek for a dual for this very simple G2 gauge theory. Okay. So how do we do that? We just follow the steps of the one-page algorithm that I have listed before. So first thing first, we talked about extracting dim-G and dim-R from A and C anomalies, but here, since the theory anyway is given in terms of vectors and fields, we know what these numbers are. So the number of vector fields needs to be 14. It's the dimension of G2, and whatever a dual gauge group is, it also has to have dimension 14. So now we just list all the possible groups that we can have and their dimensions, and we are asking this question: can we find a combination of simple gauge groups such that the dimension of them will be equal to 14? Okay. And if there is such a combination, we conjecture that there might be a gauge theory description using these gauge groups, and then we follow our algorithm either to rule this out or to find a candidate. So 14 satisfies this amazing equation. 14 is equal to 8 plus 3 plus 3. Okay. So the dimension of SU3 times SU2 squared is the same as dimension of G2. Okay. So we will look for a conformal dual for this theory, which has 1 SU3 gauge group, 2 SU2 gauge groups, and some amount of matter. As we have discussed here, the number of matter fields has to be 48. Okay. So the question is now, can we find a conformal Lagrangian theory with these gauge groups and 48 matter fields? Okay. Which will reproduce all the MC invariant information of the G2 SQCD. And in fact, we can. Okay, so here is the dual theory. So these fields are bifundamental. So I will denote these fields by Q. These are bifundamentals between SU2 and SU3. Note that the arrows are oriented in the same way. So both of these fields are in the fundamental or anti-fundamental, whatever your notations are, of this SU3. And these are the conjugate representation to this. So this will call phi, this will call phi tilde. X is a 6-dimensional representation of SU3, and X tilde is in 6 bar. Okay. The total number of fields you can count, there are 12 Qs, there are 12 phis, 12 phi tildes, and these are 6 and 6. So in total, the number of chiral fields that we have is 48, what we need. If we would orient these arrows oppositely, this will also have given us the same numbers, but it is a different theory. Okay. And this theory turns out to be not relevant, not dual to what we, to the G2 theory that we are discussing. Okay, so I will not discuss it, but it's a nice exercise to orient things differently and to repeat whatever analysis I'm going to perform and to convince yourself that you get a completely different theory. Okay, with different spectrum of operators and so on. The conformal anomalies are independent of how you orient these arrows. So the conformal anomalies will be the same, but the theory will be completely different. Okay, so now we need to, first of all, check, of course, that this theory is indeed conformal. Okay, we need to compute the one loop beta function for SU2s and SU3s, and it's a very simple computation that I list here, which you can easily compute. The only non-trivial fact that you need to remember that is that this quadratic Casimir of the 6-dimensional representation is 5/2. Okay, and knowing that, you find that all the beta functions for the 3 gauge groups are 0 here. Okay, what is the symmetry of this theory? So you have at the free point, you have an SU3 rotating the Qs, you have an SU2 rotating the phi's, and SU2 rotating the phi tildes. Again, if you would orient the arrows oppositely, you wouldn't have an SU2, you would have a U1. But here you have an SU2, here, and SU3. And also you have 2 U1 symmetries, which are non-anomalous. And I give here the charges under these non-anomalous U1s for all of the fields here. And again, it's very easy to check that these symmetries are non-anomalous in exactly the same way as we did several times before. And finally, you list all the marginal deformations of this theory. So there are many marginal deformations here, and they are written here. So for example, you have marginal operators corresponding to triangles in this quiver theory. These are gauge invariant operators. They are built from 3 free fields, so they have R charge 2, so they are marginal. So these are these operators. Under this global symmetry, they are in this representation. Okay, and correspondingly, the couplings are in conjugate representation, if you wish. You can build singlets from a cubic combination of the 6-dimension representation and 6-bar representation, which I denote by lambda2 and lambda2 prime. Again, these guys are in these representations. You can also combine 2 phi's with an x or 2 phi tildes with this x tilde to build 2 additional marginal deformations. So all in all, you have all these nice guys as your marginal deformation. And again, you have a chance of this quotient that we need to compute to discover the conformal manifold not to be empty and to have a conformal manifold. So here is the quotient that you need to compute. It looks very different from the quotient we computed for the G2. The number of couplings is different. The symmetry is different. Okay? And the representations, of course, of all these couplings are different. And we just need to compute this quotient and see whether, although the computation is different, whether the final result is the same as the computation for the G2. And this computation is, again, very simple to perform very explicitly. So you can start from these couplings, which I denoted, by lambda2, lambda2 prime, lambda3, and lambda3 prime. These couplings are singlets under the non-abelian symmetries. They are only charged under the 2 U1s. So you can easily convince yourself that there are only 2 invariants, independent invariants that you can build from all these couplings. They are written here. So this define for you a 2-dimensional conformal manifold on which the 2 U1 symmetries are broken, but the non-abelian SU3 times SU2 times SU2 symmetries are not broken. And again, there is one type of coupling which is left, which is lambda1. And you can take this lambda1 basically to the 6th power, okay? And convince yourself, it's a simple group theory exercise with hints given here, that you get a singlet. You can get lambda1 to the 6th contains a singlet of all the groups. And again, this you have SU3 times SU2 times SU2 global symmetry. This is a triplet of SU3 and doublet of these 2 SU2s. And when you turn on such a coupling, you don't break SU3 completely. You break SU3 down to SU2. Okay, again, the 3 of SU3 becomes the joint of this SU2, and the fundamentals of the SU2s become fundamentals of the remaining SU2. So the SU2 which remains is a diagonal combination of the 2 SU2s you had at the free point, and under the SU3 decomposes into an adjoint of this SU2. And it's rather easy to understand. You can think of it as a joint and 2 fundamentals, and of course you can build a singlet of SU2 here. So again, you can do this analysis of how the conserved currents decompose and how the marginal operators decompose, and what needs to be cancels out, and you are left with a single direction of the conformal manifold and an SU2 symmetry which is preserved. So again, you get a 3-dimensional conformal manifold with the preserved symmetry which is SU2, exactly as we had in the G2 SQCD. Okay. Again, we have an SU2 symmetry preserved. We need to compute its 't Hooft anomaly. Again, the computation is very different. The quiver theory is very different. So under this preserved SU2, this is a triplet. This is in a joint representation. That these 2 are doublets. So you need to combine the contributions of these 2 doublets and of this triplet into this 't Hooft anomaly. You do this very simple computation. And again, you get this -14/3 as you get for the G2 theory. Okay? If everything till now would have agreed, we would have found a 3-dimensional conformal manifold with SU2, but this 't Hooft anomaly would have been different. This would have ruled out this theory as being the conformal dual of G2. Okay? So everything, every one of these MC invariant informations needs to fit in order to for the duality to hold. And next thing, the last thing you can do is to compute the index, for example, of these 2 theories. And here I just list a couple of first terms. And again, you find that the indices of these 2 theories are exactly the same. Okay. So what is the picture then? What is this conformal duality? Okay. So now we can claim that here is a conjecture for the conformal duality. This G2 SQCD is dual to this quiver theory. We don't have a proof, but any robust non-perturbative information that you can check agrees for these 2 theories. Okay. So what is the picture that you have here? So you have a 3-dimensional conformal manifold, and this theory is nice because you can actually draw a 3-dimensional conformal manifold on a piece of paper, and you can imagine it. So you have a point on the conformal manifold where the good description is in terms of this G2 theory. So if you wish, this is our theory T1. Okay. Then we have 2 directions on the conformal manifold as we discussed, where there is a certain symmetry preserved as SU3, and then additional direction where we only preserve SU2. So on a generic point of this conformal manifold, starting from here, there is an SU2 preserved. Then there is another theory, this quiver theory that we have discussed, which it has a 2-dimensional conformal manifold passing through it with a different group preserved, SU3 times SU2 squared. And again, along the 3rd direction, the SU2 symmetry is preserved. Okay, so this is the picture. This is kind of the structure of the conformal manifold. You can make further checks. Actually, further checks are very cute to perform. I will not do it here because of the time, but you can discuss what happens with the deformations of this theory. Let me just mention what check you can perform, and please do so if this is of interest to you. For example, you can ask what happens if you give vacuum expectation value to certain operators, to certain fields. So you can give a vacuum expectation value to, say, one of these bifundamentals, and you will flow to some theory. This is a Lagrangian simple theory. You can analyze the flow. You can map this operator you gave a VEF to, find what it is, does it correspond on the G2 side, and it will be again giving a VEF to one of the fundamentals of this G2. And actually, with these deformations by the VEFs, you can explicitly show by analyzing the flow that both of these theories flow exactly to the same theory. And in fact, the theory that you get in the infrared of these flows is an n=2 theory with a decoupled free chiral field. So it's a very cute exercise to perform, you get exactly the same theory. This is yet another explicit check of this conjecture. Any questions about this?
Excuse me, does this G2 theory or the quiver theory have some 60 origin?
No. Well, I don't know of any. Okay. This is maybe the only example that I gave you in these lectures of which I don't know of a 6D origin. So as I will discuss next time, practically all, well, vast majority of strong coupling effects that we know, or dualities, AR dualities, conformal dualities that we know in 4 dimensions have a 6D origin. In fact, many of these phenomena were first predicted by looking on geometric constructions. This kind of an observation is a 4D observation of which I don't know of any 6D origin. Okay, but there might be. It's a good research question to find such a thing. One thing is, you know, engineering G2 gauge groups using string theory or geometric arguments is not that simple. Okay, so that's a thing to keep in mind.
I see. Thank you.
Again, it's not to say that it is impossible. I don't know. I just don't know how it would arise. Okay, so before okay, Babak should stop me at some point, but before I
continue, at least 10 more minutes, and then we can have questions.
So in the notes, I have written an exercise which I find extremely cute. So I will write it here. I didn't write the answer. So preparing to these lectures, you know, we have found many instances of such conformal dualities before, but you know, I thought I should come up with something new for these lectures. And actually, there is a very simple duality of this sort that I have discussed now, which has a geometric, well, at least one side of this duality has a geometric meaning, and it did not appear in the literature till now. So I will not write the answer, so you can discover by yourself something which is, well, I know this, and I showed it to Gabi Zafrir, but that's it. So you can discover it by yourself. So what is an exercise? So there is a CFT given abstractly with these conformal anomalies. And also what I tell you is that this theory has a 26 relevant supersymmetric deformations and the conformal manifold, which is 33-dimensional, on which all the symmetry is broken. There is no global symmetry. And the question is, use the algorithm that we have discussed to construct a candidate conformal dual. It's not very hard. It's not trivial. You know, the discussion we had is not very complicated, but you need to be a little bit group theory savvy. But you can perform this computation, and you can find this dual. So this is an interesting exercise to perform. And here I just want to tell you where this theory comes from. Again, for people who know a little bit about this geometric engineering, which we'll discuss next time. So this particular theory, which has these properties, is what is called the classless theory of type A2 with 3 maximal punctures and 1 minimal puncture. So you get a 2,0 theory, you compactify on a 4-puncture sphere with 3 maximal punctures and 1 minimal puncture. In this geometric language, this is a strongly coupled SCFT, okay, n equal to a CFT. But in this particular case, it actually has a large n equal 1 preserving conformal manifold. So there is an n equal 2 preserving conformal manifold, and there is an n equal 1 preserving conformal manifold. And you can actually find such a dual description. A research question to whoever is interested to do that. What happens if you have many minimal punctures and many maximal punctures? Can you find a Lagrangian? I don't know. Okay, you need to have at least 1 minimal puncture for this to be possible. So good luck. Okay, I'm not going to do that, but whoever is interested should do this, can do this exercise. And or find the dual or rule it out. Any questions about this? Okay, so maybe in the last 5 minutes, I will give a brief introduction to geometry. As Babak promised to you in the beginning that I will say something about geometry, he will not be able to stop me now. So I will say something about the geometry. So till now, we were completely in quantum field theory in 4 dimensions. And we discussed, first of all, the basic technology to address this 4-dimensional theory, and then the interesting strong coupling effects that we can discover. So next, what we will do, we will embed all this discussion into a higher dimensional setup. So let me here just discuss the basic idea about the whole of this discussion. So the basic question we want to understand, and it the question I got in the beginning about is 6 enhancement is in that vein, is okay, there are these, many interesting facts that we know about 4-dimensional theories, emergence of symmetry, duality, and so on. There are many, many sporadic examples. Can we find kind of a uniform generic setup in which we can understand all these phenomena? And then an idea to do that is to embed all this discussion into a higher dimensional setup, and basically look for dualities across dimensions. This was also a question I think I got in the first lecture. So the idea is as following. Instead of starting in 4 dimensions, let us start with our RG flow with a 6-dimensional SCFT. Okay, and instead of turning on any deformation of the types that we have considered, we introduce a geometric deformation. Okay, we introduce a scale using a geometry. Okay, we put this 6D SCFT on a compact Riemann surface, which I denote here C. So usually we had this 4D SCFT plus gauging or plus superpotential. Here the deformation is geometry. Okay, and again we do the same thing. We flow to IR. But in this geometric setup, what happens in the infrared? Since 2 of the dimensions are compact, when we get to infrared to energies much lower than the energy scale set by the size of the surface, we effectively get a 4-dimensional theory. Okay, so the effective description in the infrared is a 4-dimensional quantum field theory. Okay, so in this way, starting from 6D SCFT, first of all, we will be able to engineer a lot of quantum field theories in 4 dimensions. And the UV completion, by definition of these 4-dimensional theories, is this 6-dimensional SCFT deformed by the geometry. Okay, in principle, this SCFT can be a collection of free fields. It can have free gauge fields, and it can be interacting SCFT, or it can be a combination of these things, or it can be maybe gapped theory in some cases. Exactly the same statements hold as the statements that we discussed when we started with the 4-dimensional flow. And then there is another question that we will ask. Okay, there is this flow leading to a 4-dimensional CFT or QFT. Is there another flow which leads to the same QFT in 4 dimensions, but now starting directly in 4 dimensions? So we will want to start from some weakly coupled theory here, some collection of fields, chiral fields and vector fields, and we will have a flow directly in 4 dimensions, and we will ask, can we engineer a flow from a gauge theory here to exactly the same quantum field theory here? The properties of this quantum field theory, as we will discuss, are basically determined by the choice of the 6D SCFT and the geometry. So many properties of this fixed point have a geometric origin. And if we will be able to find a dictionary between these compactifications of 6D SCFTs and the geometry into these flows starting directly from 4 dimensions, we will have geometric understanding of various strong coupling effects in this happening with these quantum field theories in 4 dimensions. Okay, so this will be the rough idea behind the last lecture. Again, I'm sorry, it took me 3 lectures what I wanted to do in 2 lectures, and it will be only 1 lecture, but this is what we will do next time. Okay, we will try to understand this picture. how to build these dualities, IR dualities across dimensions. It's the same idea as cyber duality, if you wish, but in cyber duality, we start with 4D and 4D, two different descriptions, flow to the same CFT. Here we start, one side of the duality is a 6-dimensional theory, another is 4-dimensional theory. And here we have a geometric deformation. Here we will have our vanilla superpotential or gauge dynamics deformation. So let me stop with this introduction to the next lecture. Thank you.
Thank you very much, Shlomo. Any questions?
Can I ask you a very simple question?
Sure.
So in the superconformal index, why there's a minus sign in front of the flavor current index?
So there are two answers I can give you. One is to send you to the paper by Gade and Bim, who did that. And it's a very simple answer. Take the multiplet. So remember we have written the index as so in general you can write the index as a combination, sum of representations, or these equivalence classes of representations of superconformal group and flavor group. And just do that and ask yourself how the conserved current, n equal 1, conserved current multiplet contributes to the index. Okay. Since the index has this -1 to the f, and conserved current has, it's not just the conserved current that you know from non-supersymmetric theories, it has other components. These other components will also contribute to the index. Okay. And there will be some fermionic components, and they will contribute. And in particular, the lowest order in which the conserved current contributes is at order QP, and there is some fermionic component which contributes. Okay, and that's why you get a minus sign. Another answer, which is more concrete, you know, there was, let me give you it with the example that we have discussed. This emergent E6 here. So you can ask, as I told you, where these operators come from. You know, this comes from QQ tilde, this comes from M. You can ask me, where do these guys come from? Okay, and these guys come from very concrete operators in this quantum field theory. So again, because these have a minus sign, this needs to come from a fermionic operator. And the operator which contributes here is this Q field that we have defined times psi bar of Q. So there is a bosonic component in the superfield, which I also call Q, and there is a fermionic component which contributes to the index. That is what gives this contribution. So this is a gauge invariant contribution. This is in 6 and this is in 6 bar. So this in particular will contribute this 35. Okay. And this is what, well, this is a component of this conserved current. There will be also a -1. So does anybody know what will be an interpretation of this +1? So 6 times 6 bar is 36. It's 35 plus 1.
Just a single, that's
Yes, but what would be like, so I want to interpret this as a conserved current of SU6. What will be this? Actually, it will be -1. So there is actually a -1, which will come from this operator. So what is the interpretation of this -1?
Is the flip field?
No. Just this is the field. But what would be such? It, you know, just group theoretically, this will contribute -35 and -1. So it has to be the conserved current of this field, right? But it has an additional U1. It's not just SU6, it's U6. So this is an additional U1. And each one of these components will contribute an additional U1. This one combination of this U1 will be of this non-anomalous U1. Another combination will be the anomalous U1. And actually, you will also have here the contribution of Gaugino bilinear, which will contribute a +1. This is built from 2 fermions, so it will give you a +1. and this you can think as contribution of the gauge interaction, and this +1 will eat the anomalous symmetry, and you will be left only with this -1. So there are, it's very fun to play these games. Where do things come from? And there are various ways to think about them. As I said, very abstractly in terms of multiplets, and that's very useful. Or you can literally look, what are the fields, what are the gauge invariant operators which contribute.
I see. Okay. Yeah. Thanks.
More questions?
I have a question here. So,
Yes.
so in this case, when you compute this index, you also give us the representation. So can this representation computed from the index, or this can only obtained from the field content?
Sorry, are you asking about the matrix model? I'm not sure I understand.
No. So here for the index, you also give this representation. That's 20 and 2 here. Yes. So in this page, where you compute the index,
Yes.
you list these representations. Yes.
Can you repeat the last part of the question? Do I include what?
The representation of these groups.
Yes, the representations.
Yeah. This representation can be computed from the index computation, or you only obtain them from this?
Whether numbers or the representations. That's a question. Oh, thank you. That's an excellent question. You get the characters of the representations. Because remember, the index, we refine it with fugacities for the maximum torus of the global symmetries. Okay, yes. So you can expand it in characters of the representation of the group. So I write here just the dimensions of representations. But when you expand the index, you see the characters. You see the character of 35. You see the character of SU2 and so on. And you see the character of this representation. You don't just see 40, -40. You see the character of 20-dimensional representation of SU6 times the two-dimensional representation, character of the two-dimensional representation of SU2. Okay, so it's not just numerology. It's not just this 78. It's literally this decomposition of the character of the adjoint of E6 into the characters of the maximal subgroup, of representations of the maximal subgroup.
Okay, thanks. I see. Okay, thanks.
Thank you.
Okay, any other questions? So, Schlomo, in this characterization of these 4D theories and fixed points, you do not include defects, right?
Oh, that's an excellent question. I didn't do it, but one should do it. So there is information about supersymmetric, say, defects. You can ask what happens with them, what happens with line operators, what happens with the defects. There are certain, so you need to find some kind of, again, RG invariant or conformal manifold invariant information to capture that. For example, for line defects, there is another type of index, which is called the length index that you can compute, which actually captures the lines. And you can ask what happens with the length index. Is it equal or not? Again, the length index by the same logic is a type of Witten index, but it's a little bit more complicated. and again should be invariant of these various deformations, and it should agree between the dual theories. Okay.
And both dual theories have defects, or is it possible to have one with defect and another one?
No, no. Again, say if you have exactly the same logic as here, you know, you have this point, you compute something which is independent of the deformation. Say length index is independent of deformation, and line operators contribute to the length index. Okay, it's like if you know when you have line operators, you sometimes have a choice which lines you take and so on. But you make this choice, you compute this length index, and if this duality is correct, this dual theory has to have exactly the same choices. There should be some choice of line operators which should be equivalent, basically because you know this information doesn't depend on where you are on the conformal manifold, and then you should arrive at this point with the same information. So you should be able to get out of here with this information. So you should map on these theories. These are more complicated. So this is not an exhaustive list of things that you should match. There are more complicated things that you should match. And you know, as with other types of statements, if any one of those fails, you fail completely, even if everything else fitted. Okay, so it's important that everything will fit. Sometimes, you know, things fit in a non-trivial way, but they need to fit. Otherwise it's just wrong.
Okay, thank you.
And again, here, not everything, like in these examples, we didn't check everything. Like length indices, in some cases we did check, but not in all, because these are much more complicated computations to perform technically.
Okay, so yeah, thank you very much. I think the time is up, and yeah, people can ask more questions then later on the Slack, and we will see you then tomorrow for the last lecture.
Thank you.
Okay, thank you. See you then.
Bye.
Yeah.
See you.